Hi everyone, I'm Karen Sumwiza, and in this video I'm going to demonstrate to you how to simulate the SIR model. In previous video, Patience has shown you what is the SIR model and has come up with the three differential equations, which are ds dt, and it was assigned the negative beta s times I, where the s dt the IDT was explained by beta times susceptible times infectious minus gamma times infectious. And the RDT was defined by gamma times infectious. So in this video, I'm going to take you through how to simulate this one numerically. Now, let's see the libraries that are necessary to apply in implementing this model. And we need the NumPy library, which will work on numerical values. We also need the MATLAB library, which will work on plotting the figure, and we also need an important library, which is integrate from SciPy, and this one will help us to integrate our model with the initialized variables. Let's define our function to work on these differential equations. Define the t dx as a function which take three variables, which is x. X stands for the array of values, and t will be dependent variable. And this function is going to return an array of the three differential equations as defined before, and they will be defined as follows. Remember, it was the SDT, and it was taking minus beta times x of 0. That means that the susceptible will take the first entries of the array, and infective will take the second entries of the array. And remember, all this is divided to the total population, which is n. And our DIDT is defined by beta times x, which is susceptible taking the first entries, and infective, which is taking the second entry, also divided by the total population, minus gamma times infective, which is taking the first entries of the array, and also the last equation, which was the RDT, is going to be defined by gamma times x, which is taking the second entry of the array. After defining our function, we need now to initialize the initial conditions, which will be assigned to our function. And remember, our variables, the three variables are S stands for susceptible, I for infective, and R. And this time, at the beginning, we assume that the susceptible is taking the high number of the population, assuming that they are not yet in contact with the infective, and it is taking 99.99%. And we assume that for the first time, infective is going to take 0.001, and the recovery for the first time is taking 0, as for the first time there are not no population people that are recovered. And remember from the previous video, so the population was totaling, the entire population was totaling to S and IR, so N is equal to be S plus I plus R. And we are going to apply the initial values on these variables, where we are taking x naught as given the array of S, I, and R. And we need also to initialize these proportional constants, which are beta and gamma. Let's for the first time assign beta. Remember, beta is the rate of change of infective, and let's assign it a value of 0.5. For the first time, we see how our graph behaves. And also gamma, which is taking 0.14. From here, we also need to initialize to set to state the initials of time. As remember, this model will be, the changes will happen as time goes to see the contact of the susceptible and infectious. And let's initialize time as numpy of linear spaces, given the initial value of 0, with the interval of 100 given an array of 1,000. So we are going to work on an array of 1,000, but starting from the initial value as 0. Now, after initializing these values, now we need to do a task of integrating these values to our model. We need now to initialize it on our variable x. We define our variable x, and we call the integrate from the skippy model. We call the integrate function from the skippy library to do this integration task. Now, this time we are going to assign the initials. Remember our initial values, we have assigned them to x naught, and time is taking the initial values for the time. After setting the initial conditions of the variables, we need now to integrate these variables to the function, and we are using a skippy library to do that task, which is assigned to a variable x, integrate.audient, given the function that the x dt is our defined function and is going to be assigned some initialized values, which is x naught and time to take the time values. And also, remember, we need to plot these three variables on one plot, so we need to call them separately. So we have XIR, which is assigned to X. X this time stands for susceptible, which is going to take the first entries of the array. X, that is infective, which is going to take the second entries of the array, and recovery, which is going to take the third entries of the array. Now, after integrating our model, it's like we have assigned the values to the function where it is going to do its task, and now we need to plot these values on the graph, and we see how our model behaves. So from there, we need to define a function which is plot apd t. This function is going to take variables as x, where it is going to take the variables x, t for time, s for susceptible, infective, and recovery. So our function is going to display some of the, we are going to use some of the symbols just to represent susceptible, infective, and recovery. So it is going to plot T, like susceptible, time again is susceptible, and using those dot symbols, and also it is going to plot infective, recovery, and we need also to capture the ligand on the graph, and it is going to have to take the X labels as time and Y labels as population, where we need now to remove the borders on top and right. That is why we are having those statements. X tick is going to show the range of X labels from 0 to 100 with the interval of 10. And Y label is going to take the intervals from 0 to 1 with the interval of 0.5. And after that, we need also to set the limits of these values from X label and from Y, which is for the X label, it is going to have 100 limits, and for the Y, it is going to have the 1. So after having all these statements that will help to plot our function. Remember, we have defined our function, and we need our function to plot all these defined information, and we need also to call our function to do that task. So this statement will help us to plot.show. It's now a statement that will help us to show the graph. Now we are done with writing the codes to plot our graph, and you can see at the end we are having, if we run our program, you can see we have a graph with 3 plots. This one, remember, this one is representing susceptible. As you can see, it is coming down. It's like it is decreasing from top to down. This means that at first, remember, we have initialized it to 99%. It's like the entire population, the big population is in susceptible group. And as time goes on, as these people get into contact with the infective, it will move down. It will decrease, meaning that they are in infective group. They move to the infective group. You can see that the infected group moves for the first time. It shows that the infected group come into contact with the susceptible, and then it rises to susceptible group. Then later on, it moves down as some are recovered. Then you can see the recovered curve moving up. It shows that some people were recovered from the disease. Now, that is, remember, we get this curve, the behavior of this curve is determined by some factors like beta and gamma. Remember, remember gamma and beta, they are factors that may influence the rate of change of infective and recovery. Now, if we try to change this value, which is beta, remember it is the rate of change of infective. If we try, for example, to decrease it, let us decrease it to, let's say, 0.01, or let's take 1/3. We have reduced the value for beta, which is the rate of change of infective, and you can see now the curve has reduced. This shows that the infective disease goes down. And you can keep trying, applying different values to see how the curve behaves. Thank you so much for following. I think you have understood through this demonstration how to simulate the SIR model. So you'll keep trying. That is when you will know more how this works.